It says two blocks are connected to a light string that passes over a frictionless pulley. Looks like this.
Okay, number one looks absolutely evil.
That's what he's doing.
Yeah, you know what though? It's not that bad.
It's not. It just
No.
looks bad.
It looks bad, but it's not bad.
This really happened in real life.
All right. So here you go. It looks essentially like that. I believe our pulley is massless. It doesn't give us any mass for it. It's a black block, mass 1, lies on a rough horizontal surface as shown. You have a coefficient of kinetic friction. This block is connected to a spring. Spring is spring constant K. Second block, mass 2. It's released from rest. It descends, it stretches the spring. The spring was originally unstretched. Block M1 and M2 both move a distance h. Okay, it says, note, when block M2 reaches its lowest point, its velocity is 0. Okay, so originally, the original velocity is 0, the final velocity is 0 for both of them, okay? All right, consider the moment when block M2 has descended a distance s, where s is less than h, okay? So we're not at h, we're somewhere in between. So we're somewhere in here, okay? Not at h. At that moment, the sum of the kinetic energy of the two blocks will be given as. All right, so here we go. You want to know about kinetic energy? Let's find it. So, is this a conservation of energy problem? Is it really?
It's not at 8.
Under what conditions? Under what conditions do we have conservation of energy? What must be true?
No external forces.
Either no external forces at all or no net external forces. That'll do it. Can we go a little broader?
All conservative.
Okay, we could have some net conservative forces as long as they are only conservative forces, right? So the key thing is no net non-conservative forces, okay? So what kind of forces are causing this to move? Is the force right here that's pushing this string out doing anything?
No.
Okay, it's not affecting the motion. Is the normal force and weight here affecting the motion?
Yeah, because of friction.
Ah, not really those two, but the friction, because of the normal force, yes. So we have friction here. Over here we have gravity, but gravity is a conservative force, right? So we can convert that into, or think of that as gravitational potential energy, right? And we have a spring force, but we can think of that in terms of its potential energy, right? So the one that's killing us is friction. So we cannot say this. Okay? That is not true. That's important for you to know. Okay? It's not valid to do that. Alright? So if it's not valid to do that, then what could we do instead? We could try forces. We're looking for kinetic energy. Since we're looking for kinetic energy, that would be 1/2 mv squared. And so we could use what? F equals ma to find the acceleration of the system and then use kinematics. And kinematics would give us v, and then we could plug that in there. Does that seem reasonable? You could do that. All right. Is there an easier way?
Yeah.
How? Okay, now you've been trained to look that you have what, four major ways in mechanics to look at things, right? You have energy, you have momentum, you have forces, and you have kinematics, essentially, right? Those four major tools, right? Yeah, okay, no fluids, right? No buoyancy going on. But, okay, we need to expand our toolbox just a bit. Remember that what goes with energy is also the concept of work, right?
No.
Or just work, right? All right, so here's the deal. If we don't have conservation of energy because we have this one non-conservative force doing work, the force of friction this way, by the way, that's kinetic friction, doing work, then all we have to do is handle that little bit in terms of the work it does, right? Yes. Equals work by non-conservative forces equals how much the energy changes, right? Of all varieties. Okay? And so work done by a non-conservative force equals energy final minus energy initial, right? Okay. So if this is 0, then you have conservation of energy, right? But we don't have that in this case. We got this. So how much work is here? Fill this stuff in. Now we're looking at the system as a whole. This is for the entire system, because this is all connected. All right? So all you're doing is looking at what kind of energy you had initially, what kind of energy you have final, and how much work was done from beginning to end. Okay?
Are we using the actual end where it stopped or the distance s?
Ah, we're using that distance s, right?
What?
Because the distance S is.
Because, yeah, they throw in that little tidbit about this distance h, but they don't really use that until you get to part 2 of the problem.
Okay.
Okay? So you're somewhere before it comes to rest, or it stops, I should say. I guess in, well, yeah. I was going to say, in theory, it wouldn't come to rest, but it will come to rest.
She's talking to me.
Oh,
What's wrong with
no. Doing work. What's the non-conservative force that's doing work? Friction. How do you figure out work?
Force times
Do we need to go to do we need to go all the way to integral of f dot ds? No, because we have a constant force, right?
Yes.
All right, so it's just f dot s or d or whatever, but which way is the friction force going to be? Which way is it moving?
Right.
So what's our cosine? Theta.
180.
So it's going to be -1, right? Huh. I took care of it. All right, so there's our force friction. Force times distance, cosine theta. There's my cosine theta. What's my distance it moves? S.
No.
Now, do we need to go farther than that? And I haven't looked at the multiple choice answers.
Yes.
Yeah, just a little bit.
Do we have to go
Yeah.
mu normal force?
Yeah.
Okay, so let's go ahead and do it. So that's negative mu force normal S. We have to go farther than that?
Yes.
We have to go mg?
Yeah.
Mu, m1g, thank you. All right, is that good enough?
Yes.
Okay, so it matches up with our multiple choice. So we got the left-hand side done. Let's look at the front or the back side. What kind of final energy do we have?
You're not done yet.
I don't know. Yeah, we're not done with this.
Yes.
We got to rearrange it.
Well, there's another force causing it to move to the left.
Wait, what's
No, no,
the
no.
answer?
No, we were just doing.
We're gonna be
We're on
good.
conservative.
I hope. If this doesn't give us the answer, then it's one of those cases of we went along a lovely avenue for a nice drive, but it didn't get us where we wanted to go. So let's find out if this is going to get us where we want to go.
Can we do?
All right, and that happens. Okay? You take a nice drive. Oh, let's try this drive. Let's try this drive down this way. It looks nice, but might not get you where you want to go. We may end up having to do this. Okay, so what kind of energy do we end up with? Okay, is it moving?
Yes.
Okay, so kinetic energy. Now, how are they listing the kinetic energy? Just as a big K?
Yes.
Yes.
Okay, so kinetic energy, final, that includes both of them, okay? Is there any other energy when they're right here?
Spring potential.
Spring potential, which will be 1/2 K, ooh, S squared. All right, so that is our energy at location 2. I'll put
Why
the
is
2
it
on here.
S squared?
So we ignoring the other block?
Which other block?
Yeah.
The other one.
Yeah.
The one
Going
only,
outside.
Well, technically it has energy, is 0 energy, right?
Why?
It's moving.
It is moving.
Yeah.
Ah, but look at your answers.
All
I think it says, what's the kinetic energy of both blocks? K.
But in there, like.
So they're leaving the K as the big kinetic energy of the whole system. Because normally what we would do is we put in a 1/2 mv squared and a 1/2 mv squared for each block.
Isn't there gravitational potential though?
Ah, good question. Do we have gravitational potential energy here?
It'd be hard to determine because you don't know if that's
No, what is that?
valid.
Ah, I think I like that idea. Why don't we make this height equals 0 for this problem?
Oh.
Since we don't know how high it is above the ground, do we? All we know is that it moved from here to here, S, right? From here to here is S. That's all we know. So I think I like that. Let's see if that works out. Okay? If we call this 0, then that has 0 potential energy. Now, does this have potential energy?
Yes.
It has spring. Does it have gravitational?
Yes.
It sure does.
But
But it's not the,
Well, mg some height. What's the height?
M1,
8.
but it's
We don't know.
It's 8. H is 0.
It's M1GH, but it stays at the same height.
Okay, here's the deal. We're gonna get an mgh here for this one, right?
But it's the same for the.
And then we're gonna end up over here getting an mgh as well before and after, right? And it's not changing, right? So even though it's really there, does it really do anything in the problem?
No.
Okay, does everybody see that? That we get the same mgh here as here, so they're going to subtract from each other and disappear from the problem. That make sense?
No, wait, I'm confused. What?
Okay, look. When we're in this position right here with the red,
Okay.
they're both moving. We've called that kinetic energy. Just lumped it together. This one is attached to a spring. Its spring is stretched, so 1/2 Ks squared, right? This one is at height equals 0. This one's not. So technically we shouldn't have an mgh for M1.
Right.
Okay? Now let's just leave.
Oh, but into or.
But when you do it
Okay.
for the initial position, these numbers will be exactly the same and cancel each other out.
Right.
Okay.
Okay.
So I'm going to just show them, but then I'm going to cancel them out, just so that you can see that they're there, but they don't do anything in our problem. Okay? All right. So that's all of our final final energy. Let's look at our initial energy. Our initial energy is, we had potential here, spring potential. Now, no. Do we have spring potential here?
Yes.
No, it's an equilibrium.
Okay, this is at the equilibrium spot, right?
Oh, okay.
Okay, so that's the equilibrium spot. I guess I should put x1, so I'm calling that location 1.
There's gravitational potential.
So no spring. This one had gravitational, so that we put here, but that's going to cancel out, right?
Technically,
Does-
wouldn't both of them have gravitational potential?
Does this one have gravitational?
Yes.
Yes. What's that one?
MGS.
That's M2GS.
Yes.
That's this one's gravitational potential on G. Do either of them have kinetic?
No, because they're in.
That's where we begin, right? And then we release it. So, do you see that when we start, both have potential. When we end, this one still, M1 still has the same potential, so it disappears from the problem. And then both are moving. This is for both. I'll put that down, both. And this is the spring potential for the spring attached to M1. All right. So, let us hope that this gets us somewhere close to our answer. You rearrange that for K, I believe, correct? So if we do that, Is that one of the answers that show up?
Yes.
Yes. That's-
Well, who's going to be brave enough to try it first? Have you tried it? Does it work?
Yes.
Excellent. All right, so there's our first one. Now, do you see that this is really just an extension of what we always did last year with potential energy, with conservation of energy? We're adding on the fact that now it's not that much harder to put in a non-conservative force into our conservation of energy. It's just that now our energy is not really conserved. Our non-conservative force is changing the amount of energy, but we just add a new term right here. So it's really almost like before. This is the energy at both locations. And that's how much it changes between the two. Okay? All right. Questions?
2.
2's the same problem, except now it goes all the way to the end and stops. So what changes? Do we still have this?
Yes.
But what changes?
S becomes H.
H, H, and H.
And the
And the
kinetic
kinetic.
Kinetic energy goes away. This is no longer there. And what changes here? H. What changes here? H. Does anything else change? I think that's it, isn't it? I think that's it. Now the kinetic energy goes away because it transfers all from potential to potential, gravitational to spring. And that's correct. Look at that. All that changes is I go from gravitational potential energy here to spring potential energy here, right? That's all that changes. It transfers from one to the other, and then you lose some of that energy due to the frictional work. Okay? There you go. We got a ceiling, spring attached to it, and a mass. The spring is a spring constant K. It's hung vertically. The mass M is gently attached to it and released in such a way that the spring is unstretched upon release. The mass descends to a maximum spring extension X. Alright, so it's not stretched. So this is X equals 0 for the spring. Okay, if you drop it and release it, it goes down a distance X all the way to there. Okay, here's my first question for you. Is this spot right here, is that the equilibrium position?
No. Yes.
Whoa.
Yeah.
No.
Well,
It's the maximum spring extension.
That's the maximum spring extension. Now this thing's going to oscillate, right? Where's it going to oscillate between?
Half of that. Half of that.
Right? It's going to turn from gravitational potential to spring potential to gravitational potential to spring potential and go back and forth, right?
There's no kinetic.
Ah. Gravitational potential, and as it moves down, there'll be spring potential and kinetic and gravitational potential. But when it gets all the way down here and stops, it's going to turn all into spring potential, right? Okay, so these are like the amplitude spots, right? Positive and negative amplitude locations. So where's equilibrium?
Half of that.
It's going to be like in the middle. Okay, and we can actually figure that out exactly if you'd like. You could figure that out from, remember, equilibrium is defined to be when the sum of the forces equals 0. So that's going to be somewhere right in here when the spring force up and mg down are the same. So when kx equals mg, and this is big X here, by the way. Okay? All right. Okay. So this is our equilibrium position. Where will this thing be moving the fastest?
Middle.
Yeah, right here. Because it's speeding up due to gravity, speeding up due to gravity, speeding up due to gravity, stops speeding up due to gravity because now spring force is equal to mg, And then once it gets past here, spring force is bigger than mg, so it slows down to a stop, turns around, and then repeats on the way back up. Okay? All right, so your question is what's the speed of the mass when it's at 1/4 x? So, what's its speed when it's not here at 1/2 x, right here when it's at 1/4 x? So what's its velocity right there? Okay? All right, so here's what I did. I said, I only have conservative forces going on, right? So I said E1 equals E2. I said I have conservation of energy. All right, and so here's my location number 1, and here's my location number 2. And set those equal. At location number 1, I have only mgh. At location number 2, I said that I have 1/2 kx squared plus 1/2 mb squared. So what did I do?
But you still have some gravitational.
You set your height.
But I did this. I set my height for this problem to be 0 right there. So that's my assumption, is that right here I'm saying its height equals 0. Okay? So if I do that, then that means over here, this is mg 1/4 x. Okay? And then this over here is 1/2 k 1/4 x squared, right? Plus 1/2 mb squared. I did it just for convenience sake. Okay? Strictly for convenience. Now, do we know all of those things that we can solve all that? No, we don't know what x is, right?
That was part of it.
Oh, that was from part A. So once you know what x is from part A, you can plug it in here and then you can solve it for the velocity. Okay? And you get lots and lots of ugly math because I believe x from part A was 2mg over k.
Why is it
Okay, why is it 2mg over k?
1/2 kx squared.
Why couldn't you?
Because here, in fact, let's show that. In part A, the energy you start with at the top equals the energy at the bottom. So you have mgh equals 1/2 k x squared. How far have you descended? X. So mg capital X equals 1/2 k capital X squared. One of these x's goes away, and you end up with 2mg over k. Now I want you to notice that the distance from here to here is 2mg over k. But the distance from here to equilibrium, where the forces are equal, are only going to be mg over k. Okay, this is mg over k, this is 2mg over k. You see that the equilibrium's right in the center. Okay? And so I take this and I plug it in here, and it's going to be ugly math, lots and lots of math. You end up with some, here's what I ended up with. That my velocity equals 7mg squared over 8k square root.
You got twice what I got. Go figure.
Twice? Oh
I got
no.
7 or 16.
So you look at something by full.
Because if you include the MGH, you end up with 3/4 x, and you end up working it out to 7 or 16.
Huh.
Yeah. Oh, well.
I'll check the key. Make sure mine's right. All right. Any other questions on what we just turned in? All right. Now it's time to introduce you to rotational kinetic energy. Kinetic energy's little known, little buddy. Sure it is. Just a little buddy.
Probably
Okay, so kinetic energy is defined to be mass in motion, or I should say, the energy of mass in motion. Okay, so if you have a car moving along, its mass in motion, 1/2 mv squared. Voila! There's our kinetic energy. We've learned that from before, right? Okay, but what if you have, I don't know, here you go. How about an ice skater? And they're just spinning around. Okay, spinning around an axis. Do they have mass? Are they in motion? Yes. But this is not going to get it for us, right? Okay, I'll give you one guess.
1/2 I
Yeah,
Or I omega squared.
if translational kinetic energy, which means that all the atoms of the object move from one place to another place in unison, okay, because there is thermal energy. Thermal energy is the molecules or atoms in motion, but they're not moving in unison. Okay, they're just all randomly moving, and the object as a whole sits still. Okay, this is where the object as a whole, all the atoms move together, translate from one place to another place. That's 1/2 mv squared. But now we had rotational. Rotational kinetic energy, sometimes referred to as angular kinetic energy. Rotational kinetic energy will be 1/2, and the angular equivalent of mass is moment of inertia, and the angular equivalent of velocity is omega squared. There you go, rotational kinetic energy.
That's easy.
Piece of cake. Now, my question though is can you have both at the same time?
Sure.
Yes.
You bet.
It's just
Isn't
not
that
stable,
how
right?
tires work?
Yes. In fact, a very good one is a tire. A tire is rolling along as it translates. Okay? It's rolling along as it translates. Also, someone said a baseball. Sure, baseball is, say, spinning while it moves. Okay? Now, for a baseball, is omega and V related necessarily? No. I mean, you can throw a knuckleball, so it's kind of rotating real slow and translating. Or you can throw a fastball that would have backspin as it moves forward. And you can throw a curveball, so it spins this way as it goes forward. So the rotation and the speed of the ball have really nothing in common for a baseball. How about rolling? If it's rolling without slipping, okay, then these two are related. Rolling without slipping, we have V equals omega R, where that's my R, right? Okay, so, yes ma'am.
So the bowling ball would be just like a tire?
Yes. So, if we have a rolling object, rolling without slipping, okay, then these two, kinetic and kinetic rotational, translational kinetic and rotational kinetic, will be related because their velocity and omega will be related. Now for an object like a planet or a baseball or something like that, there's not necessarily a relationship between the two. But like for gears in a machine or something like that, then since they are like moving without slipping, then there'll be some sort of relationship between velocity and omega, okay? This will be as far as we'll go in this class. It's just velocity equals omega r. But you're, like if you have multiple gears interlocking and things like that, and things going on there, you could have a more complicated relationship, okay, like in a transmission or something.
So it has to be like, the object has to be like touching a surface.
Yes, if the object is touching a surface and it's rolling, then we'll have this relationship. but like for the Earth, there's no relationship, direct relationship between the translational kinetic energy and the rotational kinetic energy of the Earth. All right. Okay, since we talked about the rolling one already, since that was brought up, let's take a look at that one. Let's look at that on a very large scale. Okay? All right, so here's our object. Here's its center of mass, assuming it's right in the center. Okay? And as this object rolls, and we talked about this already, something rolling without slipping, then here is the ground right down here. And this spot where it touches the ground, what's it doing there? It's staying still, right? It's stationary with the ground. So it's important for us to remember that if we have rolling without slipping, there's no work being done by static friction. Static friction implies no motion, right? So if there's no motion, then there's no work done by friction, which is kind of weird. So when something rolls, in theory, it should roll forever, right? Because there's no negative work done by friction. Okay? All right. So the velocity right here is 0 at the point of contact. Or I should say velocity equals 0. All right? So this is our pivot point. Okay? This is our pivot point for the object. Right here. Okay? Now, about this point, is the object translating as a whole? Or is this pivot point translating? Not at that instant in time, right? This point right here is touching the ground and not moving, right?
Right.
So, here you go. You can view, here, let me back up for just a second. I think I confused some people. All right, let's look at an object. Let's look at like a baseball, all right? A baseball that's moving through the air and rotating. Actually, let me do backspin on it just so that you don't think it's like rolling without slipping. Okay, a baseball is moving through the air. Okay, does the baseball have translational kinetic energy?
Yes.
Okay. Does the baseball have rotational kinetic energy?
Yes.
Okay. So what we have to do to find out the total kinetic energy, what we have to do is add up the two. Okay? So we'll have 1/2 mv squared and 1/2 I omega squared. And we have to add those to get the total. Okay? So here's my question. Velocity of what point on the object are we interested in? The center mass. Because remember, for translational motion, we're talking about the object's center of mass. All right, for rotational motion, about what point are we going to calculate our for our rotational motion, about what point are we going to calculate our rotational kinetic energy? The axis about which it's rotating. Okay? Question is, for a baseball flying through the air, what is the axis about which it's rotating?
It goes through the center.
It goes through the center of mass, right? An object under free rotation will rotate about its center of mass. And so this is for the center of mass, and this is for the center of mass. Okay? All right, now, let's look at a different object. Let's say we have that problem that we had before where we have this meter stick pinned to the wall and it's going to rotate downward. Okay? Is the object, well, the object's moving, going to move, right? Okay, now so it has kinetic energy. What kind of kinetic energy? Got to vote for rotational. Does it have translational?
center mass is moving from.
Okay, here's the deal. Here's the deal. There is a center of mass for this object, and the center of mass will translate, right? It will move. But here's the kicker, everybody. When you calculate the total kinetic energy, your reference point for translational and your reference point for rotational have to be the same point,
Like the center of mass.
like the center of mass.
Or we could choose different.
Or you could choose a different one,
Even if it's rotating around. the
as
point.
long as you choose the same point for both.
So if we choose
Now-
the side, we don't have to use the translational?
So that's my question. If we choose the center of mass, does the center of mass translate?
Yes.
Yes. Is it spinning?
Yes.
It's not really spinning about that point though, is it?
No.
But it is, that point is not, its orientation about its center of mass is not the same though as it moves, right?
Right.
The center of mass is in the center here, here. Here's the center of mass right here. It looks like that to begin with, and afterwards it's down here. So I mean there has been some rotation about this point, right? That makes sense? Its orientation about that point is no longer the same, right? Okay, but could we pick a different point,
Yes.
which is a nice convenient point?
We could be a pivot point.
Okay, is it rotating about the pivot point?
Yes.
Sure. Is the pivot point translating?
No.
No. So if we pick a different point, if we pick the pivot point, yes, we have rotational kinetic energy, but we have no translational kinetic energy about the pivot point. The pivot point is not translating. Okay?
What if it is?
What if it is?
Then it just is.
Like that one. See this one? See our pivot point? Our pivot point is translating, right? So we have to include both kinds. Alright? Now, let me show you how these are going to be the same. Okay? Let's do this. Let's look at the one about our pivot point first. So our total kinetic energy is K rotational about this point. Okay? So that's going to be 1/2 I omega squared. Alright? That's I for moment of inertia about that point. Okay, but I want to move that pivot point. Where does this pivot point come from? Remember our parallel axis theory? Parallel axis theory says the moment of inertia about any point equals the moment of inertia about the center of mass plus md squared, right? Okay, now watch. So the moment of inertia about this point plus md squared. So what's d here? That's 1/2 the length of the whole thing, right? So if I do this, and I substitute this in, but this is going to be about my center of mass plus m, and I get 1/2 L squared. Okay? And I plug that in, this in for this. I'm running out of room, so I'm going to put it down here. I'm going to plug this in right here for this. I'm going to rewrite it down here. So my total kinetic energy is 1/2, and then I get moment of inertia about the center of mass plus m 1/2 L squared times omega squared. Okay? Yes?
Shouldn't it be 1/4 L squared since the 1/2 is squared as well as?
Yeah, that's squared.
Oh, no, he put it in parentheses.
He wrote
Yeah, I got it in parentheses.
At
It would be
the
like
first line he wrote.
up at the end. just
Oh,
squared.
there.
Right there, yeah.
Sorry, thank you. All right? So I get 1/2, I'm gonna multiply everything out. So I get 1/2 I about the center of mass, omega squared, plus 1/2 m plus 1/2 L squared times omega squared.
Wait, where did it be 1/4?
Ah. In parentheses. Right? A bunch of ah! There you go, you're right. Got it. Got it, got it, got it. Okay. What's that?
Oh, is that
No.
Oh,
Omega times r. So omega squared times r squared gives me v squared. But velocity of what point? What is this the radius to? The center of mass. Does everybody see that this is the radius to the center of mass times omega? Radius to the center of mass squared times omega squared, which gives me velocity squared, but velocity of one particular point. This is 1/2 mv squared for the center of mass. So what did we just prove? We proved that,
the total kinetic energy.
yes, that the total kinetic energy for an object, any kind of object, here I'll make some strange random object.
An elephant.
So some strange random object, and if you have a pivot point right there, and here its center of mass is right here, and it's rotating about this pivot point, okay, omega, then if you want to find the total kinetic energy of this object, K total, you can either do one of two things. If there's a pivot point that's not translating, you can do this. K rotational about the non-translating pivot point. Or, what could you do? You could do K rotational plus K translational about the center of mass. Either one will work. Now, which one is easier?
It's rotational about that.
If you have the moment of inertia about the pivot point, then it's easier to just do rotational about rotational kinetic energy about the pivot point. That's easiest. But in order to do that, you need to know the moment of inertia about the pivot point. So if you have some odd-shaped object where you don't know that, then you're better off translating it to the center of mass, and if you know that one. So it depends on which moment of inertia you know. Okay? It won't really matter. They'll all come out to be the same. Now, let's do the same exact thing for this one. Okay? Actually, you know what? I guess I don't need to do the same exact thing for this one. This ball rolling without slipping. Technically, it's rotating omega about this fixed point. That point is stationary in space for that instant in time about which it's rotating about that point, which is really odd. So you could do one of two things. For a rolling object, you could do this. For a rolling object, you can do the rotational kinetic energy only, but you have to have the moment of inertia about this point. Now, for most rolling objects, do we have the moment of inertia about this point? No. Most rolling objects, we know the moment of inertia about its center of mass, right? So, for a rolling object, it's almost always going to be easier for us to do this. Find the rotational kinetic energy about the center of mass, and then find the translational kinetic energy of the center of mass itself. Okay? So you have those two options for an object. If we have an object like this baseball flying through the air, and the baseball's flying through the air, and it has an axis that's translating, and there is no stationary axis, okay? If there's no stationary axis, like we have for this object rotating down, or this object, then you just have to add up the two types of kinetic energy, okay? You don't have the option of finding a fixed point that's not moving, about which the entire object is rotating. So you cannot do this only if the object itself is propagating along, okay? All right, how we doing? You doing okay? So, by the way, everybody, that is essentially rotational kinetic energy, all right? Just picking the appropriate spot for which to calculate the kinetic energy of the system. Yes, ma'am. Who? All right, everybody. Here we go. We have a pulley and a mass hung from it. This has a radius of r. This has a mass of m. Let's see, what did I put for my moment of inertia here? Oh, this moment of inertia of this thing is 2/5 mr squared. That's what the moment of inertia of this thing is. All right? Okay, this thing's going to descend a distance d. All right, I want to know how fast it's going when it reaches that distance. Okay? All right? Now, we've seen this problem before. We've solved this problem before. And when we solved it before, we solved it with forces, found the acceleration, and once we found, well, forces and torque, you're right. We had forces and torque, and once we found the acceleration, we used kinematics to find out how fast it was going when it got here. So we could easily do that. Okay?
I'm ready.
That's not.
All right, I want you to solve it that way first.
Which way?
With forces and torque and acceleration and kinematics. Solve it that way first, and we'll solve it with energy second. Yes. Hey, we're finding that our rotational dynamics is kind of weak, so let's practice it, okay? We're finding, sorry, that's a good question. When it gets right here at the bottom, we want to know what's the velocity of the object. So what is the velocity? Velocity equals, I don't know. Here we go. Velocity equals... there we go. That's what we're looking for. Where do we start?
Sum of forces.
Okay, we got to have a couple free body diagrams, right?
Yes.
Okay, so here's our one free body diagram. mg, we got tension, We've got a force up this way as well, which I'll just call the vertical force. And we don't know the mass of this thing, but I do have the moment of inertia of it, right?
So, but there's a weight there.
Yeah. Oh, yeah. Thank you. There's an mg here. Thank you. Sorry about that.
So,
Of which I don't know what that m is. Yeah.
Not that I can-
okay, so
Yeah, not that I
when
care.
you know the mass, you can then plug it into the mass, to the m.
If I know the mass, m, yes, you can plug it in. That, well,
Because last time you said not to plug it
The moment of inertia.
No, not to
in. Well, the
I.
last problem, because we had some.
Not to the. You don't plug it into the I. You plug it into the mg of the pulley, but not the I.
yeah. This I is given. The moment of inertia is given. This mass actually here, we don't know. I didn't give you that. Okay? But if it was m, then this would have been a 2/5. That would have been a hollow sphere, right? Okay. All right. So where do we go from here? Okay.
Sum of forces and sum of torques.
Sum of the torques equals I alpha for this one. The sum of the forces equals ma for this one. Let's do the torques first. How many torques?
1.
1.
RT.
RT. And this is 2/5 mr squared alpha. Okay, for this one,
MG.
we have an mg minus t equals ma. Okay? We're looking for a, but we don't know t. So what do?
Alpha equals.
Alpha equals.
Okay, we change this. Alpha equals a over r. Oops, over r. We plug that in, and we get RT equals 2/5 r squared a over r, and then lots of magic happens, right?
All our R's.
All the r's disappear, and we're left with that t equals 2/5 ma. So we can plug that in here.
Are we saying they have the same mass or different masses? Because then we wouldn't be able.
The pulley and the weight.
The pulley and
Same variable m. How's that?
Okay.
Yeah.
See, because that way it's simpler.
Yes, it is. Yes, we will assume this m and this m are the same m. Thank you. M and m, thank you. So we got mg minus 2/5 ma equals ma. So that means mg equals,
7/5.
thank you, 7/5 ma, had a brain fade. So a equals 5/7 g.
Yep.
Does that make sense?
Yes.
5/7 g.
Much like-
Much.
5/7 make sense?
Yes, it's almost free falling, but it's had some.
Okay, so it's less than free fall, so that should be good. Because if it was 7/5, then we knew something would be wrong, right?
The pulley's making it.
Yes. We'd have, right.
It's throwing it
It
down.
would be accelerating you down.
Oh my god.
But that
I'm
still
not
wouldn't
getting
work.
to that
But
yet.
like
I'm
as
not
the
The
getting-
pulley
pulley
could
is
have a
throwing
motor.
it down.
It'll be a winch instead of a
Yeah,
pulley.
but if this is accelerating or spinning around so that's letting out rope faster than mg, the rope would just go slack.
It's not
This
a
is
rope.
not gonna.
It's not a rope. It's a wire. It's a wire that's throwing it down.
It's a rigid wire. Right. Okay, now, that's not what we want to know. We want to know velocity.
V squared.
V squared equals V naught squared plus 2ax minus x naught, but x minus x naught for us is h. Oh, sorry, it's d, right? That's d. Our initial velocity is 0, so velocity equals 2/5/7 g times d square root.
Yeah, 10/7
10/7 GD square root. There you go. Wow, that's a lot of work.
Not really. I
I'm ready
enjoyed
to
that.
do a.
You ready to solve it the easy way?
Yes.
Yes.
All right, do we have any non-conservative forces?
We'll say no.
I like your way of thinking. We'll say no unless otherwise stated. There's no drag, right? Please, no drag. No
I
drag.
forgot about drag.
No friction is listed here. So energy 1 should equal energy 2. What kind of energy do we start with?
Gravitation.
Gravitational. Now, where are you going to call height equals 0?
At the bottom.
Or D is.
Yeah, nice. So this has gravitational potential energy. Does this have gravitational potential energy?
Yes.
You bet.
No.
It's just not happening.
But is it changing?
No.
From when this mass goes from here to here, does this gravitational potential energy change?
No.
No, so does it show up in the problem? Does it do anything?
No.
No, it shows up on both sides and gets subtracted out of both sides, so it disappears. So we're going to pretend it's not there.
I like that idea.
Yes.
Like
We just know it's not going to do anything, right? So what kind of energy do we start with? Just mg d. Okay, what kind of energy do we end with?
Kinetic and.
Kinetic of both.
Yeah. Yeah.
Now, this has kinetic when it descends. Translational. This has kinetic as this descends. The pulley has kinetic. But that pulley kinetic will be rotational only. This will be translational only, right?
Yes.
So we're going to end up with 2 kinetic translational for the box plus kinetic rotational for the pulley.
Yay.
Okay? So we end up with mgd equals 1/2 mv squared plus 1/2 I omega squared for the pulley, and this is for the box. Okay?
Okay.
Can we do better than this?
Yes.
We can change omega into V over R or V squared over R squared. We can change I into 2/5 mr squared with a 1/2 out front. So it looks like this, and a lot of things go away now.
Yay.
Yeah. M goes away. The 2 goes away.
Go away.
The R squareds go away. And I'm left with GD equals 1/2 V of the box squared plus 1/5
Yes.
V squared of... Is that V squared of the box? Are they the same V's?
Yes.
Yeah, because the speed at which the rim of the pulley is rotating is the same as the box descends, right? All right, so GD equals 7/10. Or the velocity equals 10/7 GD square root. Voila!
Much faster.
And a lot more elegant, actually, as we like to say in physics. It's a nice, elegant solution. Not so much getting the sledgehammer out and pounding away until you get the answer, which is what we get sometimes. We don't have any choice. We like the elegant solutions because we're lazy, for the most part. It just seems nicer and prettier on our paper.
Less chance to mess up.
Exactly. And we like less chance to mess up.
Look at my.
Whoa! Hang on. Okay, when we say elegant solution, we do not mean this. This is very hard for a grader to grade.
Sorry.
How do you understand it now?
You can read that?
In all honesty, though, if you get the right answer, it doesn't matter.
They look.
I thought that, like, for grading fast, they would just.
Well, they look.
Ah.
Make it easy. Make it easy on the grader.
Giant answer, and then like.
That's right.
Last time I talked to a table reader, they said they look for the correct answer and then correct supporting work. If
Yeah.
it looks like it's the correct type of work, they'll take it.
Yeah. Essentially,
But if
you
it's
know, because
not,
they're grading
uh-uh.
thousands of papers. And so they'll go through, and the first thing they look for is the answer. If the answer's correct, they'll look back, and they'll see, oh, okay, that looks about right. But if the answer's there and no work, you'll get like 1 point for the answer, and then nothing else.
If that.
Yeah, if there's no work at all, I don't know what the ruling on that is, whether they give you any credit at all.
I don't know how.
No?
How can you do it?
I don't know why you would do that. It's like.
I have students in Physics B doing that right now. It's like they're punching it all in on the calculator to put an answer down, and there's like a couple of numbers. You'll see something like a 1/2, and then you'll see 10, and then you'll see 9.8, and then all of a sudden down here you'll see 57 newtons, and you're like, and this is much more scratched out than that. I mean, it's not nearly that lovely looking. And that's their answer. And they'll be nice and they'll box this, but that's the wrong answer. And I look up here and I have no idea what that is. So I can't give them any credit, which is really sad. Because a lot of times, they know what they're doing. They just haven't shown the thought pattern. That's what you got to show the grader, is your thought pattern. Okay?
So should I include like just the random thoughts?
And right now I'm thinking of
Do what I
meal
showed you to
covered
do
in
in
lilies.
pre-AP. That's why I showed you how to do it in pre-AP.
All right. Work equals, well, okay. Well, let's do this the down and dirty way here. Work equals FD, right? But you can say distance is equal to R theta, right?
I sure can. Bro.
So if I rearrange that, that's torque and that's theta, right?
Bro.
So that's work. Now that's not really the way you should derive that. You know, math and physics teachers would be mad at me, but there you go. This is work when you're rotating something. Because think of it, if work in translational motion is a force through a distance, then work for rotational motion should be a torque through an angle, right? Torque through an angle is the rotational equivalent of force through a distance, all right? So there's work. So it's torque through an angular displacement. All right, so let's talk about power. Power is work over time. Power is the change in energy over time. Power is force times velocity. Okay? All right, and I got one more for you. Hey, very good. It is torque times omega. The angular equivalent of force is torque. The angular equivalent of velocity is omega. So if you apply a torque at a certain angular velocity to keep it moving at that rate, then that's the power. All right, so we have a new one.
All the curly hues.
Yes. All the curly hue. All right. So,
So just for, and here's a crazy thought.
uh-oh, this is the place for it.
Maybe it's not crazy. If I have like a pulley or whatever,
If you have like a pulley or a pulley.
it's like one. I have a pulley. Yeah.
Yes?
And there's friction at the axis, right? Work
Right.
is being done by the friction.
Yes.
But like if I use torque theta, there's no radius, right?
Sure
Or how
there
would I
is.
do that?
There's a little radius.
Like tiny.
So, if you want to have a pulley that has minimum frictional work done, okay, then first of all, you want to have as little friction as possible.
Right.
But if you can only eliminate friction down to a certain amount, you know, then you would like your axle to be as small as possible.
But support the weight.
Yes. Right. The smaller your axle, up to a reasonable limit, you will have less radius for your frictional torque or frictional force to work through that radius. So you have less torque, less effective torque.
But like in our imaginary pulleys where the axis is like non-existent, right?
What
You can't
number?
have friction work against it.
In our imaginary pulleys, yes. Now, that's the next step. I mean, if you go farther than this, is you'll notice that now our pulleys have mass, right? But our pulleys don't really have friction, right? Now, in the real world, they will. They'll have a couple frictions. They'll have friction from the rope or string or whatever laying on the top, and they'll also have friction on the axis, okay? And, you know, in a real pulley, you know, that axis, that pulley is centered by two objects on the end, keeping the pulley centered on the axis. And so it can rub up against those as well. So you got lots of places for real friction. But when you get down to that level of technicality, you're into engineering. I mean, you're applying the things we already know for a practical purpose. So, and you just take, what we have is enough to get you started in that arena. Okay? All right. We are just about out of time. I wanted to do a couple of things.
Watteau.
Okay, let's do this.
Watteau.
Mr. Gruen,
Yeah.
can I have my yellow sheet back? It's pretty bad.
Your other sheet back.
Yellow one.
Why?
It's pretty bad. I'll rewrite it.
What yellow one?
Okay, here you go, everybody. I have this meter stick, and just because I wanted to be different this time, I'm going to have the meter stick all vertical-like. And then I hold the axis, and then I let it swing all the way down. I'd like to know how fast is it going when it's here. That's question number 1. And when it's here, that's question number 2. And if I was really mean, I'd have some kind of angle. Or I'd ask you, can you develop an equation to tell me the velocity at any angle?
Are you gonna be very mean?
Yes, it's very possible.
But Mr. Brown,
Actually, it's not that hard. You would not want to solve that with forces, would you? No. Okay? Because you're looking at angle, and forces would give you acceleration, which would relate it to time, right? And then you'd have to relate it through kinematics to location, and lots of work. Plus, is your force constant on it? No.
it's based on the angle.
It's based on the angle. So that would be a very challenging problem. So we don't want to do that. Whenever it looks really challenging, let's think, that looks hard. Can I solve this with energy, or energy and work? In this case, assuming no friction, I would suggest you solve this with conservation of energy. And go. You're solving for its velocity. Here, I'll make it easy on you. What's the omega here, and what's the omega here? So omega at location number 1, at location number 2, it starts off at the top with an initial omega of 0. So I won't even have you figure out the velocity, because the velocity will be different at different points, right?
Yeah.
If I just said, what's the velocity at location 1, location 2, if you really want to be a smarty pants, what could you say? You could say 0, but you'd have to qualify that. 0 where? At the pivot. Haha, I win. Right? So on the exam, they'll say, what's the velocity of the center of mass? Or what's the velocity of the end of the meter stick? Because those are different things, right? All right, so figure those two out, please.
So Mr. Brown,
Yes. Okay, has anybody figured out that needs more information yet?
Okay, I would really.
What do you need?
You don't know where to start.
with the.
What energy
I
does it
I see a lot of you have drawn nice figures
But
here.
if it doesn't start-
Okay, well let's start with the concept of, is there any work done by non-conservative forces?
Gravity.
No, there
Oh,
is
no.
Gravity is a conservative force, right?
Oh, non-conservative.
Now wait a minute. But, there are other forces, right?
Gravity, normal.
There's a force here at the axis, right?
That's velocity. We're finding a W.
Yeah, but there is a normal force or a vertical force keeping that thing from falling, right?
Yes.
But the thing is that that force is not moving through a distance, is it? So is it doing any work?
No.
No. Okay. So the only force that's moving through a distance is the gravity force, right? So that's conservative, so we're in good shape.
Wait, why
So-
is it normal working through a distance?
Because the normal force, this force at the hinge is not moving.
Oh, okay.
So you have force, but no distance, so no work. Okay?
Oh, okay.
Got it?
FD.
Yes, FD.
Okay.
FD cosine theta. So, and if there's no friction there, there's no torque, right? There's no work done by frictional torque. So we're in good shape to use this. So first big step is to say, I can use conservation of energy. These three should all be the
I
same.
actually have more than that.
Okay, what kind of energy do I start with?
nothing.
Gravity.
Gravitational.
But it's weird.
A weird gravitational energy.
Okay, we have a change in height
yes, we do.
of the center of mass. Now, everybody, you need to be careful of making sure that you're keeping track of this point,
Yeah, that's weird.
because the center of mass is what we're concerned with in potential energy, right? Okay, where do you want to call your 0 point?
At
Center.
the center.
Pivot.
For fun. Fun.
You want to pick the pivot? All right, I'll choose that. That's fine. I think you're crazy, but I'll choose that.
Let's pick the bottom.
Actually, that's a really nice spot if you're going from here to here. If you're going from here to here,
At the bottom.
then you might want to pick the bottom, right? So you might want to change your 0 point depending on what location you're interested in.
Let's pick the
So if we're
bottom.
interested in this spot right here, then we'll choose that as our 0 point. So we're just solving for the first one then. What kind of energy do we start with then?
MG
Mg.
L over 2.
Okay, we need some numbers here, right? Okay, let's just do MGH and then we'll decide what we need. Okay?
And you're ending in 1/2 MV.
And when we get here, we're ending with
1/2 MV.
1/2 MV squared?
And 1/2 I.
Oh, because it's rotation.
Yeah.
All right. We're ending with kinetic at this location. The question is what kind of kinetic? Is it rotational only?
Around the pivot point.
Yeah.
It's rotational only if you choose the pivot point that's not translating.
Yes.
Or you could choose the center of mass, in which case you would have translational and rotational. So which do you want? Let's choose pivot point. I think that's a nice one to choose. So this is rotational only about the pivot point. Okay, so that should becomes mgh equals 1/2 I omega squared about the pivot point. And so now we need some information. Okay, let's say the mass of this thing is m. Let's say that its length is L. Let's say
Its
that...
height is H.
It hurts to laugh.
Hi, Andy. Yeah, its voltage is V. Its volume is capital V. Has a capacitance of C.
What
All
about
right.
density?
Oh, a density of rho. But it has uniform.
Oh, thank you.
Stop. Well, we can see.
Uniform density.
So if you change it,
Throw some water in there.
All right, so there you go. Anything else you want to know?
I
Oh my god, that'd be a horrible problem.
And you'll notice that as it moves from this location to this one to this one, that it changes colors. It starts at brown, changes
So
to
is that a
green,
cork
ends
thing?
with red.
Because the color charge is changing.
Well, it is rotating quite fast, so we do have some
Doppler.
Doppler shift.
Oh my god. If it makes noise, then we can do
Like,
like
if it's emitting a sound,
it makes a sound.
well, where
Yes.
do I observe
And
it?
as it descends, it goes,
And it loses mass.
It's crumbling as it falls.
It's actually straw filled with water. And so
oh,
wouldn't that be really cool?
I think that would hurt my brain.
Okay.
Okay, so here we go. So then, okay, what height is this then?
L over 2.
So mgl over 2. What I do we have? What moment of inertia?
It's at the
1/3.
pivot point.
1/3.
So 1/3.
1/3 ml squared omega squared. Okay, now you can solve it, right?
Yeah.
How come you couldn't solve it before? I don't get that.
Because
We didn't
Oh,
have
we just assumed
brains
everything.
behind
Well, we
Yeah.
assume it
The 2 can go away, and what one half is that?
Oh, yeah, we can take this 2 away and leave this with a 3.
Yeah.
and we
We can get rid of one of our L's.
Wait,
Get rid of an M.
Why are we, what?
So we get a 3g over L.
Add an equal sign.
Why is that L over 2?
but that I don't get it. That doesn't
Does that work?
I don't, wait, why is that L over 2?
vary.
G equals
What do you mean it
1/3
doesn't vary?
LW squared.
Is this right?
Oh.
you tell me.
I don't know.
It's always
3G, bro.
Teach me.
no,
Is that right?
Did it have any close to that when we did it?
What do you
Yeah.
mean?
I get one head going, whatever.
We got something close to that when we did it.
You got something close to that?
But
Before we did before the
right, as that says, it
Before
doesn't, it
the
doesn't
L over
change.
2 thing.
before the L over 2.
Okay, Mark's brought up a really good point.
But
Mark said, yes.
it would vary because at any other point, it wouldn't be at a height of 0, so there would be gravitation.
Okay. The question was, but that doesn't change. It's moving through it. It shows us constant velocity. But that velocity or angular velocity, that angular velocity we calculate is only good for
That 1 point.
this one point. Okay? Now, you see how this L over 2 will change as we move to a new location, right? Okay, so when we're here, this is our angular velocity. Okay, now, what's our angular velocity going to be at the bottom?
0.
Well, you could use the same equation or you could change your h.
I'm going to use the top to the bottom, and I'm going to do mgh equals 1/2 I omega squared. But I'm going to have a new location for my 0 point. I'm going to call this my 0 point now. If I do that,
Now your h is L.
Now my h is L. I get mgl equals 1/2 times 1/3 ml squared omega squared.
How is this H, but not all L's?
Oh, my m goes away.
So you have.
Is that right?
Yes.
Yes.
Okay.
Root 2.
Now, I have 2 assignments for you.
Oh, go right.
We already have no homework.
You already have e-homework. Oh, no.
Okay, one, I don't work today, but I do.
Okay, assignment number 1 is derive an equation that will tell me at any angle theta what the omega is.
What? Say what?
Wait, what?
Say what?
What?
That was cool.
Read that again?
Okay.
I want this. Omega at any angle theta equals
Oh.
what?
Something G over.
So like if it happens to be here or here or here or here. So when it's here at 90, assume this is theta. Okay, so when it's at 90, you better get this. When it's at 180, you better get this.
Okay. And then with drag and friction, we have to find out what angle is delta.
No drag or friction. That would be too rough. Why would I want to do such a thing to you?
What's the second assignment?
Friction.
What's the second assignment?
All right, that's our only assignment.